So what have we learned so far? We've learned that the energy of electron orbitals is dominated by electrostatic attraction between the electron and nucleus, that the electrostatic attraction depends on the distance between the electron and nucleus and the amount of shielding, and that the lower the energy, the more stable, and the more stable orbitals are always filled first. Today, I thought we'd talk about energy of electron orbitals and the periodic table. And again, to understand atoms, molecules, chemical reactions, we have to understand electrons and how they're distributed in atoms and molecules and their relative energies. The difference in how elements behave is due to the difference in their electron configurations. So with that information, what we want you to be able to do is determine the number of valence electrons and core electrons and whether or not an atom or ion is paramagnetic or diamagnetic. I want you to be able to determine the electron configuration of atoms and ions using the periodic table. And I want you to understand that elements in a group have the same valence shell electron configuration and hence have similar chemical behavior. So we've already seen that electrons fill the lowest energy orbitals first, and they fill orbitals following Pauli's exclusion principle and Hund's rule. Remember that Pauli's exclusion principle says that each orbital can have at most 2 electrons, one with m sub s plus a half, one with m sub s minus a half. Hund's rule says that each electron gets their own orbital when the orbitals have the same energy. The energy level of the orbitals depends on electrostatic attraction between the electrons and nucleus. The larger the effective nuclear charge, the stronger the electrostatic attraction, and the lower the energy. And the effective nuclear charge is affected by how many protons in the nucleus, but also how much shielding. Remember, electron density can be shielded from the nucleus by other electron density. The closer electrons to the nucleus, the stronger electrostatic attraction, and the lower the energy of the orbital. The lower the energy orbital, the more stable. So we can actually put all that into this flow diagram. And again, you see the smaller the n, the closer electrons to the nucleus, stronger electrostatic attraction between the electron and the nucleus. The more protons in the nucleus, the larger the effective nuclear charge, the stronger electrostatic attraction, the less shielding, the larger effective nuclear charge, the stronger the electrostatic attraction. The stronger electrostatic attraction, the lower the potential energy of the orbital, and the more stable the orbital. Now, if you think about this, because of these ideas, each element will have a unique set of energies for the electron. And so the larger the n, the weaker the attraction between electrons and nucleus, hence the higher the potential energy, and the less stable the orbital. And again, we saw in terms of shielding, s orbitals are shielded less than p's, which are shielded less than d's, which are shielded less than f. And so in a shell, and a shell member is denoted by n, here n equals 3, the d are higher energy than the p, which are higher the energy of the s, because the d gets shielded more. You should also remember that the shielding changes a little bit as you fill these orbitals, and so eventually the 4s actually becomes higher in energy than the 3d. And so it's kind of cool that this video is actually based on fairly high quality calculations, and it shows you how the energy levels of the orbitals actually change as you go from one element to another element. And so the energy here is in absolute terms, and so you can compare from one element to another element. And so it's kind of interesting, if you look at the 1s orbital, it keeps them going down in energy because as you have more protons in the nucleus, you're going to have a stronger effective nuclear charge. 2 electrons per orbital, that's from Pauli's exclusion principle. And here, those 3 have the same energy, and so each electron gets its own orbital as much as possible. And so the lowest energy orbitals are always filled first. And so for hydrogen, you have just 1 electron. That one there is the atomic number, it's the number of protons and number of electrons for stable atoms. And so you have just 1 electron, it just goes in the lowest energy orbital first. And so we'd write down the electron configuration, 1s1. This one corresponds to n. N equals 1 here, 2s, n equals 2, 3s, n equals 3. The s is related to L. So for L equals 0, that corresponds to S. And then the superscript tells you how many electrons in the subshell. And so the 1s subshell has 1 electron for hydrogen. Hydrogen atoms are paramagnetic because they have an unpaired electron. And so if an atom has 1 or more unpaired electrons, it's paramagnetic. It's going to be attracted to a magnetic field. If an atom has all paired electrons, then it's going to be diamagnetic. It's going to be repulsed by a magnetic field. And so helium, it's element number 2. You have 2 electrons. Again, Pauli exclusion principle says that you can put a maximum of 2 electrons per orbital, one with m sub s plus a half, one with m sub s minus a half. Now this is diamagnetic because all the electrons are paired. Lithium has 3, and so you have 2, 3. You can do a maximum of 2 electrons per orbital. You got an unpaired electron, so if you have 1 or more unpaired electrons, that would be paramagnetic. If we go beryllium, that has 4 electrons, 2, 4. They're all paired, so we'd say atoms of beryllium are diamagnetic. If we go to boron, we see we have an unpaired electron, and so that would be paramagnetic. Element number 6 is carbon, so 2, 4, 6. Notice that the 6th electron goes here, so the 2p orbitals all have the same energy, and so each electron there gets its own orbital when possible, and that's referred to as Hund's rule. And so to determine the electron configuration, we just fill the lowest energy orbitals first. And the number of electrons has to equal the atomic number if it's charged neutral, if it's just an atom. Now this is our electron configuration, 1s2, 2s2, 2p6. And so the numbers in front correspond to n. So 1s, that means n equals 1. 2s, that means n equals 2. 2p, that means n equals 2. S corresponds to L0. P corresponds to L1. D is L2, and F is L3. And the superscripted numbers correspond to how many electrons are in that subshell. And so we'd say this is a shell. We'd also say the 1s is a subshell. The 2s2p corresponds to a shell. Remember, a shell is denoted by the end, but we'd say that 2s is a subshell and 2p is another subshell. And so we have 2 electrons in the 1s subshell, 2 electrons in 2s subshell, and 2 electrons in the 2p subshell. And so the Bohr model, you have the nucleus, and so for carbon you have 6 protons. Atomic number 6 means 6 protons. Most carbon isotopes have 6 neutrons. And then we got 2, 4, 6 electrons. And so in the Bohr model, you're talking about shell. So you have 2 electrons in the first shell, and then 4 electrons in the second shell. And so that's how we draw the Bohr model. Now the Bohr model is not very helpful. Again, it's kind of confusing. It looks like the electrons are in orbits. Remember Heisenberg's uncertainty principle. You cannot know the position and momentum of an electron simultaneously. And so it's kind of interesting. You have the Bohr model. You have the atomic orbitals. Now remember, superposition means that the electrons can be in multiple states at a time. And so because electrons are in a superposition of states, atoms by themselves are actually spherical. And so we can look at nitrogen. We have 2 in the 1s, 2 in the 2s, 3 in the 2p. Remember, half-filled subshells a little extra stable. And so nitrogen's actually a little bit more stable than you would expect otherwise. Nitrogen is very paramagnetic. The more unpaired electrons, the more paramagnetic. Oxygen atoms are also paramagnetic because you have unpaired electrons. If we go to fluorine, we have a single unpaired electron, and so that is also paramagnetic. And so if you have one or more unpaired electrons, that is paramagnetic. If all the electrons are paired, then it's diamagnetic. Now we got to neon, and so neon is noble gas. Elements in the farthest right column are noble gases. All their subshells are full, and that leads to very stable configuration. And so noble gases are not very reactive. There are no known compounds with helium or neon. There are actually a few known compounds with argon, krypton, and xenon. But in general, they're not very reactive at all. And so atoms tend to lose, gain, or share electrons to get noble gas configuration. And so if we look at the periodic table, we can actually determine, the last orbital occupied. So here we're occupying the 1s, or I probably should say the last subshell occupied. And this would be the 2s, 3s, 3s, 4s. Here the last subshell occupied is the 2p, and these are the 3d. And so the electron configuration matches, the order of filling matches the periodic table. Right, so on the bottom we have the order of filling, and again it's just based on lowest energy orbital first. And so 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, etc. And so as long as you understand how the energy level for the orbitals fits to the periodic table, you can use the periodic table to actually determine the electron configuration of atoms. Really pretty straightforward. And so you should be able to determine elements electron configuration using the periodic table. And so the energy levels map onto the periodic table. Now the rules that we're talking about in terms of the order of filling, there are some exceptions. And so the ones in red are the exceptions, and you're not going to be responsible for the exceptions. And what happens here is for like krypton, it actually is a little bit more stable to have 5 electrons in the D and only 1 in the S. Same with molybdenum, it's more stable having 5 in the D and 1 in the S. For niobium, it's happy with having 5 in the D and none in the 5S. And so type of question you could see in the very near future would be, what is the electron configuration of sodium? Now you're always given a periodic table. On all exams, the front page has a periodic table, and so you need to be able to use it. But to be able to use it, you have to know that sodium is Na. And so I want you to know the names and symbols for the first 36 elements. And so sodium is Na, it's right there. And then we just go, okay, 1s2, 2s2, 2p6, and then 3s1. Now another way of doing electron configuration is, if you notice you have 1s2, 2s2, 2p6, that's actually electron configuration of neon. So we could also say neon 3s1. Now then the square bracket always has to be the last noble gas, and so that's why we can go neon 3s1. And finally, is sodium paramagnetic or diamagnetic? And so you got an unpaired electron, and so it has to be paramagnetic. So this question asks us, what element has the electron configuration 1s2, 2s2, 2p2? Now it's very important that you understand how the periodic table relates to electron configurations. Remember that here you're filling the 1s2, here you're filling the 2s, and then here you're filling the 2p. Now 2p2 means you just got to carbon. So again, make sure that you understand how the periodic table relates to the order of filling. 1s2, 2s2, 2p2. So this question asks us, what is the electron configuration for sodium? And again, you should know the names and symbols for first 4 rows of the periodic table. The periodic table is not very helpful unless you know that, say, sodium is Na. And so again, we have 1s2, 2s2, 2p6, and then 3s1. So here asked, are the atoms of boron or oxygen paramagnetic or diamagnetic? And so paramagnetic means you have one or more unpaired electrons that's going to be attracted to a magnetic field. And so if we think about boron, it's right here. And so for boron, you have 1s2, 2s2, 2p1. And so it's got one electron in a p orbital, and so boron would be paramagnetic. For oxygen, you got 1s2, 2s2, 2p4. Now you got to remember, for the p's, you got 3 orbitals, and so they get their own, each electron gets its own orbital as long as possible. And so the oxygen is going to have 2 unpaired electrons. And so atoms of both boron and oxygen have unpaired electrons, and so they're both going to be paramagnetic. And so again, if you have one or more unpaired electrons, it means it's paramagnetic. And so this one asks us, are atoms of carbon and nitrogen diamagnetic? And so diamagnetic means that all the electrons spins are paired. And so for carbon, we're right here. And so carbon, 1s2, 2s2, 2p2. And again, if we think about the p's, there's 3 p orbitals. Each electron gets its own orbital as long as possible. That's Hund's rule. And so carbon is diamagnetic. For nitrogen, 1s2, 2s2, 2p3. It's right there. And again, if we think about those p orbitals, for nitrogen, each electron gets its own orbital. Again, that's Hund's rule. And so in this case, neither atoms of carbon nor nitrogen are diamagnetic. Both atoms of carbon and nitrogen are paramagnetic. And so how many unpaired electrons does silicon have? And so again, please make sure you know the names and symbols for the first 4 rows of the periodic table. That's the first 36 elements. You're always given a periodic table, but it's not very helpful unless you know the names and the symbols. Now we could do this one a little bit differently. If you remember the energy level diagrams, you got 1s, 2s, 2p, 3s, 3p. So silicon is element number 14, so it's got 14 electrons. So 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And so it's got 2 unpaired electrons. And so atoms of silicon would be paramagnetic. So valence electrons are the outer shell electrons that dominate chemical behavior. And so what we can see here is, remember, shells determined by n. And so here's n equals 1, that's the first shell. Here n equals 2, that's the second shell. And then here n equals 3, that would be our third shell. And so we have electrons in the third shell. There's 2 of them, so we'd say there's 2 valence electrons. Now an electron is either a valence electron or a core electron. And so magnesium has 2 valence. And then it's got 2, 4, 6, 8, 10 core electrons. If we look at chlorine, it's got 2, 4, 6, 7 valence electrons and then 10 core core electrons. Again, please remember that an electron is either a valence electron or a core electron. If we look at calcium, it's got 2 valence electrons, again, outer shell electrons, and so that means the shell with the biggest N, and the rest of these will be core electrons, and that would be 18. Now it's kind of interesting, notice that we put electrons in the 4s before having any electrons in the 3d. It's a little confusing. The D is higher energy than P, which is higher than the S because of shielding, and that actually ends up putting the 3d higher than the 4s, and so the 4s gets filled before the 3d. But as you fill 3d orbitals, you can actually sometimes bring this energy level down, and the 3d will be lower than the 4s. But in order of filling, we always consider the 4s being filled before the 3d. And so what that means is that the 3d, the d electrons, will never ever be valence electrons. Outer shell, biggest N. And so you're going to put electrons in the 4s before the 3d, and so 3d will never be valence electrons. For a similar reason, F electrons will never be valence electrons. They're never on the outer shell being biggest N. And again, an electron is either valence electron or core electron. It has to be one or the other. Also notice that the core electrons do not always correspond to a full shell or to noble gas configuration. For calcium, the core in this case corresponds to the noble gas configuration of argon, but not a full shell. And here we're looking at bromine, and so your core electrons are here, and that does not correspond to noble gas configuration. And so here where we're looking at calcium, the core electrons did not correspond to a full shell because you didn't have the 3d. It did correspond to the noble gas configuration of argon. Here where we're looking at bromine, the core electrons actually correspond to the electron configuration of zinc. So it's not a noble gas configuration, and it's also not a, I guess in this case it is a full shell. But it does not have to be a full shell, does not have to be noble gas configuration. Now the concept of the core versus valence electrons is most important for what's referred to as S block and the P block. The transition metals here in the middle behave a little bit different. Now it's easy to determine the number of valence electrons. It's actually just equal to the column number if you ignore the transition metals. And so this column has 1 valence electron, 2 valence electrons, 3, 4, 5, 6, 7, 8. Now these last 2 columns you have to be a little careful. I mean, hydrogen obviously has just 1 valence electron. Helium has 2, but below the hydrogen these halogens would have 7, and then the noble gases except for helium would have 8. But the column number gives you the number of valence electrons. And so if we look at germanium, it has 4 valence electrons. The rest are core. D and F electrons are never valence electrons because they're never in the outer shell. Now all elements in a column of the periodic table have the same valence electron configuration and hence tend to have the similar chemical properties. And so again, please remember the valence electrons are important because they typically dominate the chemical behavior. And because elements in the column will have the same valence electron configuration, they'll have similar chemical properties. And so this question asks us, how many valence electrons does an atom of titanium have? Now please remember, you need to know the names and symbols for the first 4 rows of the periodic table. You'll always have a periodic table for your exam, but it's not very helpful unless you know that, say, titanium is Ti, and it's element number 22. Now the valence electrons are the outer shell electrons. Now, one way of answering this question is to do electron configuration. And again, you should know how the electron configuration maps onto the periodic table. And so for titanium, 1s2, 2s2, 2p6, 3s2, 3p6. Now remember, the number in front corresponds to the n. L equals 0 corresponds to S, L equals 1p, L equals 2d, and the superscript corresponds to how many electrons in that subshell. And then you got 4s2. And then for titanium, you have 3d2. And so it's a little confusing. Again, the number in front, that's the n. It's not the row. And so even though this is the fourth row, in this region here, the 3d orbitals are being filled. Now the valence electrons are the outer shell electrons, largest n, and so that would correspond to the fourth shell, and you just have the 2 electrons there, and so titanium has 2 valence electrons. Now in general, all the transition metals are going to have 2 valence electrons. If you remember, there is some exceptions, in how they're filling. So like 1, 2, 3, 4. Chromium, I think, is 4s1 3d5, and that would be 1 valence electron. But following the rules, and in general, the transition metals will have just 2 valence electrons. And so this one's asking how many core electrons does aluminum have? And so aluminum is Al, and it's very important to remember that either an electron is a core electron or it's a valence electron. And so maybe the easiest way of doing this one is, again, doing electron configuration. So 1s2, 2s2, 2p6, 3s2, and then you'd have 3p1 right there. Now, valence is the outer shell, and so the third shell is going to be our valence shell. And here, this is going to be our core. And so the electron is either going to be part of the core or it's going to be a valence electron. And so we have 10 core and 3 valence electrons. And so this question is asking us, atoms of which of the following element has the most number of valence electrons? And so one easy way of remembering is that elements in the column have the same valence electron configuration, and so they're going to have very similar chemical properties. So the first column, they have 1, second column 2, 3, 4, 5, 6, 7, 8. Obviously hydrogen is just 1 and helium is just 2, but the elements below hydrogen and helium will be 7 and 8 respectively. And so boron should have 3 valence electrons, carbon should have 4, nitrogen 5, fluorine has 7, and neon actually has 8. And so if you think about neon, its electron configuration is 1s2, 2s2, 2p6, and so valence is outer shell, and so that would give you 8 valence electrons. And again, remember, the importance is that the valence electron is actually where the chemistry occurs. So elements tend to gain, lose, or share electrons to get noble gas configuration, and typically that involves the valence electrons. So Lewis diagrams help keep track of valence electrons around atoms, ions, and molecules, and help us predict structures of molecules. So if you know the number of electrons in the valence shell of an atom, writing Lewis diagrams is relatively easy. Lewis diagrams are used primarily for S and P block elements. It's essential that you learn how to draw Lewis diagrams. Whenever you're doing chemistry, you will always be doing Lewis diagrams. And so if we look at oxygen, its electron configuration 1s2, 2s2, 2p4, 1s2, 2s2, 2p4. We could write the Bohr model this way, and so oxygen is element number 8, so it's got 8 protons. The most stable isotope has 8 neutrons, and so you got 2 in the first shell for n equals 1, and then you got 6 in the second shell, n equals 2. Now, in terms of Lewis diagram, we only look at the valence electrons, and so that would be in the outer shell, the 2s and the 2p, and so 2, 4, 6. And so we'd have 6 electrons in the valence shell. Now for a Lewis diagram, again, you only look at the valence electrons. A single dot represents an electron alone in an orbital. A pair of dots represents a pair of electrons sharing orbital. And so you can imagine that, say, these 2 electrons correspond to these 2, and maybe these 2 correspond to those 2, and then these 2 correspond to the 2 that are by themselves. Now, which side you put the electrons does not matter. The following are all equally valid. You notice that in all 5 cases, we have 2 pairs and 2 lone electrons. Again, 2 pairs and 2 lone electrons are consistent with the valence electron configuration that we see when we do the energy level diagrams. We can also look at the elements in the first 3 rows of the periodic table. And again, I mentioned that elements in the column behave alike because they have the same valence electron configuration. All the elements in the first column have 1 valence electron, second column 2. Now we're skipping the transition metals. So this column has 3, 4, 5, 6, 7, and then 8 if you ignore the helium. And again, elements in the column behave alike because they have the same valence electron configuration. And so we can draw the Lewis diagram. We can see how it is related to the Bohr model. The atomic orbitals indicates where the orbitals are, where the electrons reside. And again, remember that electrons are in a superposition of states, and so atoms by themselves are actually spherical. And again, it's important to remember that elements in the column behave alike because they have the same valence electron configuration. And so we actually organize groups of periodic table elements in the column. And so in that first column, we have alkaline metals. The second column, we have alkaline earths. These are the transition metals. The far right are the noble gases. The second to the right is the halogens. And then the third from the right are the chalcogens. Now, there's a line, a diagonal line that goes down that separates out the nonmetals from the metals, and you have some metalloids. And so we don't really have a name for these 3 columns because you have nonmetals, metalloids, and metals on those 3 columns. They don't behave alike as much as the other columns. I should also point out that hydrogen is not a member of any group. It's kind of by itself. Often it's here because sometimes it forms a +1 ion. Often it's here next to helium because sometimes it forms a -1 ion. But you should know the names and valence electron configuration for the different groups. And again, when we say group, we typically mean columns. And so hopefully you can determine the number of valence electrons and core electrons and whether or not an atom is or ion is paramagnetic or diamagnetic. Hopefully you can determine electron configuration of atoms and ions using the periodic table. Hopefully you understand that elements in a group have the same valence shell electron configuration and hence similar chemical behavior. I hope that helps.